Thank you very much for inviting me. I can't say how impressed I am with all the presentations that have been carried out so far. 20 plus years ago, I was the PhD researcher in the dark room who was looking at cine film water droplets that had been measured with a copper vapor laser. Cine film was run at 7,000 frames a second, so I was recording 0.7 of a second and observing, 300 drops on a film, and it would take me a few days to count those drops and to record the velocities of each of those drops. And then those drops would then go into a model, and it would take several more days to try and put that information into a model, and that model was very simple. And I avoided all the film break-up parts because we didn't know how to do that, so I was further away. So it's just lovely to see how the whole world has progressed. So that was me 20 years ago. Since then I've been doing more practical stuff, so more fire modelling, more seeing how the sprays influence the burning properties of fire. And I've also done a lot of gaseous extinguishing, so I've not sort of been in the water mist or sprinkler area all the time. So what I'm coming to talk to you today is about water mist. We've had a lot about sprinklers, and to some extent water mist sort of should be a simpler problem. Going back straight onto the droplets, the droplets are smaller, and so perhaps they're more understandable. So I'm talking today about water mist, so I will start going through the properties of water mist, and we've all had a great introduction, so I'll try and cut that down to just what's relevant to water mist. And then I'm going to report on a research project we've done looking at the use of water mist on building fires. Water mist has been around perhaps for about 20 years, and its development has all generally been towards the ship industry, so looking at flammable liquid fires in engine rooms, and looking at quite controlled environments, quite often flammable liquids, not always Class A environments. And in the UK, there's a desire to move away from sprinklers, perhaps more towards more efficient designs of water delivery, so that you could perhaps look at smaller tank sizes, use less water, and use it in a more engineered manner. So there is a move to using water mist in sprinklered areas, and the concern is, will they work as well? Will they be as reliable? So the work was part initiated by the insurance industry and part the building control area, where they said they were meeting the use of water mist in areas with large rooms, tall ceilings, and they were feeling a bit unsure about whether the technology would work as well as sprinklers or was appropriate for those sorts of uses. The research project we undertook was about a 3-year research project, and I'll talk you through that. And then it has fed into what we now have is a British standard, what's called a draft for development, which aims to standardise, if it's possible, water mist as a technology so that it could be seen as equivalent to sprinklers. So just on the properties of water mist, the difference between sprinklers and water mist essentially is the droplet sizes are smaller. So if you've got your 1 millimetre droplet and you smash it up into much smaller droplets, say about 100 millimetres, you've got 1,000 more droplets generated from that one droplet. And that 1,000 more droplets presents a much bigger surface area, so you've got 10 times the surface area, which means you've got 10 times the efficiency of the heat mass transfer. And another aspect that Ron mentions was the mass transfer. So you change the water liquid into water vapour, and then people quote values like it takes up 1,700 as much volume of water vapour compared to the liquid. The other angle to this is you've got your smaller droplets, which means that when they're travelling in space, they've got less of their own momentum, their terminal velocity is less. So your big sprinkler droplet travels nicely down to the floor, and so terminal velocities, it travels about 4 metres per second. So that can travel down into perhaps the seat of the fire if it's big enough. Your smaller droplets have got much slower terminal velocity, and so they're travelling 100 millimetres, travels about 25 centimetres a second. When you're down to 20 microns, they're only going about a centimetre a second. And that can be good for removal of heat, because it means they're resident for a much longer time in space, but it can be poor from the ability to get to the fire. So often, or they can be pushed away and dependent on the fire flow that they're within. And so from a water mist engineer's perspective, they do need to understand these criteria, and hence the attempt is to design methods to ensure you can deliver the water onto the fire so they've got enough momentum either through high pressure pushing, or sometimes they talk about seeding it with large droplets that creates a dynamic flow that encourages that. So we haven't seen many videos, so I'm quite pleased to be the first to get a video working. This is a picture of a water mist nozzle. It's like a sprinkler one, but as I said, they're usually charged at a higher pressure, so the water is forced out of the nozzle faster, and there's smaller orifices, so the holes that they go through are smaller. The general thought is that water mist completely fills the space, but in actual fact they can be quite sort of tight columns of water, and actually they're only protecting a sort of 1 metre column below themselves. And you get the benefit of filling a greater space when you've got compartment walls, and you've got the water mist pushed out to the sides and falling down after a period of time. So that was a demonstration. I don't know how clear it was, but we were looking up at a ceiling with 4 nozzles on. That's the single nozzle in a compartment, and that's the 4 nozzles. And although you do get the columns of water, you do get a little bit of infill, but some of what you see there is just a visual optical illusion. They were distinct sprays. We've done a lot about the mechanisms of fire, so I won't dwell on this. Fire control or fire suppression. So droplets basically removing heat, conduction, convection, radiation, and their benefit is, and they fall and they wet surfaces, and they can also evaporate and displace oxygen sort of near the fire zone. Things to be aware of in the compartment, things that we've observed is in the compartments you do get the water droplet filling, and then that can inhibit spread by removing radiation or just general cooling. But equally they are still droplets. There's a great desire to think of them as gases. They do actually fall, and we've not really observed much pickup of them going underneath tables to try and cool and extinguish fires under tables. So we carried out a research project. It was funded by BRE Trust. I work for BRE, I don't know if you know who we are. We used to be a government organisation looking at building fire protection. We now not government funded. We also used to have LPC as one part of us, which is where I came from, which was funded by the insurance industry. So our role is assistance with research and testing for government bodies like the MOD sometimes, like the built environment, and also we also look at the environmental side of things too. And all the profits that we make, we then plough back into ourselves, so we're a not-for-profit organisation. And so this was one of the large projects funded by the profits, as is supporting universities. So what we've tried to do is, as I said, there's a lot of work being done with flammable liquid fires, and we were wanting to look at the Class A fire, the area that we perceive to be more difficult for water mist. We looked at low pressure systems and high pressure systems, but mainly low pressure, because that's generally what might be considered to be used in Class A fires, Class A being solid combustibles, if you don't know. And a lot of the work was done with single nozzles, although some 4 nozzle testing was undertaken. Where we carry out the work is in our burn hall, which is a large facility, nothing to compare with FM's. 15 metres by 40 metres by about 50 metres tall. But it does have a controlled airflow, so we can control the inlet and the outlet air, so we can represent much bigger spaces in the area. We have a movable ceiling, so this is what we were looking at before. It's a 6 by 6 metre ceiling on legs, and again we can use that to represent a larger space if you can put a representative number of nozzles on it. So a lot of the work was done in the open space, but we also did some in a compartment. To undertake the work, lots of research testing with suppression extinguishing systems is with fires that are fully developed. So if you're doing fire extinguisher testing, you get a whole crib of light and you're looking at trying to extinguish that fire. If you're doing gaseous extinguishing testing, you put a heptane pan in, you're trying to get the heptane pan alight. With water mist, one's aware that you're not necessarily going to be extinguishing the fire, you're actually trying to suppress the fire. And to some extent, you want to find some way of gauging how well you're achieving that. So the idea we came up for this project was to use a crib, but just to light it at one end, so that, and for it to be able to spread to the other end. So we're looking at the prevention of horizontal spread. And so we did a few trials to find the best arrangement of crib. We came up with what you might consider a relatively small fire size, 0.5 megawatt, where we lit the crib at one end, and then it would take about 20 minutes to burn through to the other end. So our test protocol for our early stage work was with a wood crib. What we would do, we'd actually light it early, let it to spread for about 10 minutes, and then we turn on our water mist nozzle and we look at the relative performance when we change some of the parameters. So we looked at different parameters. I don't know how much you know about the water mist industry, but the water mist is very much manufacturer owned. So manufacturers understand their own products, they understand they've done a lot of testing to understand their limitations, and the industry works on the basis that you have to prove that you can control a certain fire type. And when you prove that you can turn that certain fire type, the system that you've designed has to be the one that you then go out into industry and use. So some of these parameters which are understood by manufacturers aren't necessarily understood by people who are then going to be approving and specifying and checking them. So for instance, nozzle spacing is understood to be important. Just with sprinklers you put them at certain spacings. Nozzle flow and pressure is expected to make a significant change. If you have a lower flow, you get bigger droplets. The use of compartmentation has an effect, ventilation, and also ceiling heights. So all these parameters will affect the performance of your water mist system. Another thing I've highlighted at the end is the fire hazard. When you're developing a fire test, you've got to be sure that the test is a reliable, repeatable test and actually will continue to burn for the period of the test period. So for all tests, it's quite easy to set up something that looks very realistic, but actually it's got vulnerabilities where the fire can grow and then can sort of fall back down again and then start to grow if it's able to spread to the next item available to burn. So what we thought is important to do is to ensure we had a fire burning regime that was reliable and repeatable. So I'm not going to go through, so it's a big research report, and obviously you never do everything you want to do, and you can't do as many tests you want to do, and so ultimately we ended up for each parameter just doing about 3 tests, sort of the best case, worst case, somewhere in the middle, to see if we got the feel of the trend of what was happening. So this is a test, just to give you a feel. This is a wood crib test where the wood crib is placed directly under the water mist system. With water mist, as I showed you, it's a neat column of water, and so you'd expect the water to be delivered well into that area. So we've got very good control, well, really we've got extinguishment, and we measured the temperature above the crib, and also at the ceiling, which was 2.5 metres up. So with directly under the crib, we've got very good control. at 1.25 metres offset from the nozzle. Again, we had control. It wasn't as good as the other area. So we were sort of just on the edge of where you could see where the mist was being delivered. And we got quite high temperatures above the crib. But I mean, you could definitely call that control and suppression. But when you move just 60 centimetres away, which from a designer's perspective isn't really very much, you were really moved outside the spray plume, and you got to the point where you had no control. You had big flames coming up from the crib, and arguably it was an unsuccessful fire suppression. And so we carried out this work in some respects just to point out to everybody that these small details actually will have a big impact. If you carry out that same test inside a compartment, so this is obviously a bad slide, but with the crib up against the wall of the compartment, so our compartment size was 1.85 or whatever, for radius, I suppose I should say, so twice that in diameter. You carry that out inside a compartment. Your crib is not so easy to see, but you do get control, and the rest of the crib is burnt. Above the crib, we did get high temperatures, and in the ceiling layer, we also got higher temperatures because we were containing more of the heat. But I would say it was a better situation from the perspective of the water mist's performance. Another thing that I alluded to earlier was obstructed fire lanes. So in real buildings, in offices, if you do just look round, there's a lot of the fire lane is not nice in a nice open clear space. Actually, it's under tables, on shelves, in cupboards, under chairs. And so you do get fire loads that is obstructed, the water mist can't see directly. And if you put the same wood crib underneath a table, you really do get no control of that wood crib. And so if that's the only thing in the room, perhaps that would be okay. Measured 850 degrees above the crib. But actually, in a compartment space, we've got all the mist contained within the compartment, and we were actually measuring ceiling temperatures of about 40 degrees. So it was, you could argue it was a success because you'd actually created a situation where you weren't going to get flaming beyond the compartment. We looked at ventilation, and here we had a relatively small ventilator blowing at some distance away, but perhaps we got up to about 3 meters per second in some areas, sort of listed in our results. And what you find is the ventilation has two effects. It does affect the fire, so your fire spread across your crib is increased. But equally, I don't know how well you can see this here, but with ventilation, actually, most of the drops actually get blown away. And in all our tests in the open space, like I say, we had no control. The fire continued to burn every time, and that's with the fire directly underneath the nozzle. So ventilation, I wouldn't say we've done it completely, but it really is a significant factor, and that really has to be understood by all. When we carried out ventilation in the compartment, to some extent, I suppose this was a much better result. So not only did as I said, you interrupt the burning of the fire, you also get sort of circulations within the compartment, which arguably keeps some of the mist in place. So when we carried out sort of stylized setups within the compartment, we did get control at the 1.85 distance away, and we had the crib beneath the table as well. So it was a challenging situation, and I would say with ventilation in the small compartment, we got control, reduced temperatures at the ceiling. We carried out this with a low pressure system, but we also used a high pressure system where you've got much smaller droplets. And in this case, I would really contest that we didn't have control, and we had very little suppression. We had flames, where it's gone grey, all the plywood's burnt away, so there's actually nothing left to burn. So we had flames continuing throughout the period of water spraying. So just in summary, of our parameter study, which was very much small scale wood crib. It'd be lovely to have done bigger cribs, it'd be lovely to have done other fuel leads, but we were just investigating the parameters so everybody would have a feel and the data could be available for people to use in the future. Most important, the spacing, pressure and flow. In our testing, we didn't challenge it to a great degree, and we didn't find, we found differences, but not to the degree that the dead was spacing and equally in ceiling height. We found differences, but they weren't as significant as the spacing issue and the ventilation issue. So the second phase of the work we did the parameter small scale, and then we embarked on the office scenario, which was of greatest concern to us. To set up a fire test, we felt it was necessary to go and see what the hazards should be like, so we were fortunate enough to be taken by an insurer to a trading room that is no longer running anymore. And in these areas, and these are places that have been proposed for the use of water mist, they are ginormous rooms. They have very long desks and connected space that is obstructed. And then there are other areas where they've got high ceilings, minimal fire loads. You've got your cabling areas in much tighter spaces. And this was a sort of a battery backup area where all these plastic contained batteries are within a space. Water mist arguably might not be the best solution for all these areas. You might look at gas, for instance, in this sort of in the higher fire load space where you're actually wanting extinguishment. So the other thing with water mist is very application specific. So we were trying to sort of find a way of moving more to fire engineered values for it. So you could look at fire loads and determine a mass loading of a space and try and relate that to the use of a water mist for equivalent spaces with the same mass loading. So we looked at, we've got a database of design fires where we've run many different types of fires and looked at the calorimetry problem. We also looked at standard fire tests. Also, the standard fire tests have come from the IMO arena. And they don't always present the most challenging of tests. They present very open surfaces that the water can get to with small amounts of obstruction. The corner test, to some extent, is quite good because you can get vertical spread as well as horizontal spread. But it's a very exposed test from the perspective of water mist. So here are just the plots of heat release rate from a burn of an office arrangement. This was quite a low fire loading office arrangement, but we got, this was not my work, it was done 10 years ago, peak heat release rates of about 4 megawatts. Classically, everybody thinks of an office fire as a medium growth rate fire with 25 kilograms per metre squared of fuel, that sort of thing. If we look in the British standard for fire engineering, those are the values that you'll find there. So we developed a fire load that that was stylised, but the intention was it would reflect what you'd expect in an office. So we've got if you go from the start of fire to the peak, we've got about a medium growth rate fire, and we could argue that where it picks up actually is a faster fire. This corner bit targeting is not perfect. This is where got some foam rooms on the desk, and they're meant to be targets for looking at spread. But they get involved. We started the fire in the corner, so we get the sort of the hottest fire burning quite early in the fire. This is a view at about sort of, I think about 3 or 4 minutes. And the intention of the fire is you'd light this crib, and it's a crib of wood and polypropylene, and then it would have the ability to spread along the crib. And then it would also, if it was hot enough, have the ability to jump over to the next crib. And then you'd also have, this is plywood, and it's thick plywood to ensure there's enough fuel left. You'd have plywood to do the upward and the horizontal spread as well. So that was the plan with the fire arrangement. So I'll just give you, I don't know, this about 3 minutes, so if you get bored, just raise your hands and I'll politely move on. This is a view of the fire test that we set up. The time starts at 0, and this time here is going to skip through because I've tried to speed it up a little bit for you. Don't know if we get noise, it's best if we don't because you might whistle it. So this is the crib operating, and this is a demonstration test that we did with a low pressure system. I think we put it on YouTube so you can watch it at a slower rate if you want at a later stage. In this test we got the ceiling at 5 metres above the crib, and so 5 metres above the crib. And so the time of sprinkler operation, which is about 5 minutes, the fire has consumed half of this crib. It's burning up through the corner, and it's just about to spread to this crib here. We had thought that the sprinklers might have operated a little earlier, and so we've got the polypropylene here burning on the top of the crib. And so our plan to see if we could prevent a spread across some of it was negated by the slowness of the operation of this system. So at this point here we've got, I don't know if you can see, this is the mist coming down now. So the ignition source was in the middle of 4 nozzles. And so you can see all the mist coming down, so all 4 are delivering onto our ignition source. Is that the end? That is the end. So what happens is you get water delivery, this area here all becomes effectively extinguished. You get continued burning underneath the crib. We carried out this setup. This was about developing a test for standards. So we carried out this setup for 7 tests. We did an initial test with sprinklers just to confirm that we were not producing a fire test that was beyond the realms of a sprinkler. So we used a quick response sprinkler with perhaps normal water delivery to 5 millimetres a minute. And what we found was, this is while water mist was, when the sprinkler was running, what we found was we had some damage above the table, but we still had quite a bit of the cribs intact underneath. And this plywood is all black, so it's charred, but it's not burnt away, it's not destroyed. What was measured, we had thermocouples. I don't know if you can see that line, oh, there, that one there. That's a tree with thermocouples on, so that's for measuring temperature. So at 2.5 metres, which is about here, we were measuring 40 degrees in the corner area, and at the ceiling about 40 degrees too. So we've got very good control, very good suppression. With one of our low pressure systems, again we had equally good results. We had control, well, extinguishment really, I would say, of the top area post once the water started being delivered. Temperatures very good, we're a bit below the sprinklers this time, 20 degrees rather than 40 degrees at those 2 locations. And we really had no spread to the ends. All the plywood is intact, so we haven't really burnt through the depth of the fire layout. So perhaps I want to point out. So this is a water mist system, and what's good about water mist is the assumption that you use much less water. In this arrangement, which was our successful arrangement, actually the nozzle spacing was just 2.5 metres apart. And they were running at about 30 litres a minute, which gave us a water delivery rate of 5 millimetres a minute, which is the same water delivery rate as required for sprinklers. So to get an equivalent test result, actually we needed the same amount of water as you do for a sprinkler. And we did obviously run more tests at other flow rates. So when we ran at a flow rate of 3.5 millimetres a minute, so that's on a 3x3 spacing, we we really did not get what we would consider acceptable suppression and control when compared with the sprinkler case, if that's what you're planning to replace, uses the replacement technology for protection of offices. So we had a reduction of the temperature in the corner of 300 degrees, so that was reduced. The ceiling temperature 100 degrees, again that's reduced, but we are 5 metres up, and that's quite a long way. And the damage was quite extensive, so all the plywood is completely burnt through and fallen away above and below the table, and we've got flaming during the test projecting beyond this first burning item. And so it would create arguably a hazard to the next thing that would be available to burn. It is with this test, it is quite a challenging test. You might want to imagine it as you know, the sort of the baseline, the most severe test that you might do in the water system. We also looked at high pressure systems. And I suppose the other thing I should say, that these are generic systems, they're nobody's in particular, but they are the industry systems that throw out water mist in a sort of an understood standard way. When we carried out the high pressure systems, we did have problems with pumps and all sorts of things. But when we ran in this scenario with a 3x3 spacing, 2.8 millimetres a minute, so similar to the low pressure system that wasn't working well, we really had very little fire control, so we had continued burning in this fire load, and we had flaming the edges of the fire load, and all this obviously has been destroyed in the test. So we've got 300 degrees, 90 at the ceiling, and an awful lot of damage. And we, from our perspective, look at this, declared that was a no control. You could argue there was some level of control because you actually got cooling in the space. So it was better than the free burn arrangement. The other thing I should mention, because I know people here are interested in sprinkler skipping, some of the tests, what we found was with the high pressure nozzles, we were only getting one of the nozzles operating. And so within the test, we introduced a 30-second delay, which ensured there was enough heat to pop all four nozzles. And so it gave it the best chance to deliver water onto the fire load. In other tests, we did stop the water and wait a few minutes to try and pop some more heads so that we could actually offer the water system enough time to deliver onto the fire load. So this is the high pressure system. I'm just going to show you the 5 minutes. So 5 minutes was quite consistent for all the tests, the time of operation of the mist system. So this is at 5 minutes with the fire burning underneath, and this burning really triggered by the fire load under the table. So I don't know how well you can see it here, but where we felt it was failing was it just didn't have enough momentum. So there was water mist coming out from the ceiling, and a lot of it, I mean, maybe we were unfortunate where we placed the fire load, but a lot of it you could see was just pushed the other side of the wall system of our fire load. And so you could argue you're making that the outside a fire-safe environment, and you really weren't affecting any control in the area of the fire. So in summary, we carried out a series of tests of the water systems we tested, and there were only a few, and there probably are much better things on the market. Only one of the arrangements resulted in good suppression control. And the other arrangements, in our opinion, failed to sufficiently suppress the fire. And some of the things that we altered were things like spacing and flow rate. And these are absolutely critical. You really need to deliver enough water onto the fire. So I don't know, as an audience, how interested you are in what's happening with British standards. I sit on the British standards for water mist commercial. We also have another one standard for domestic. And in Europe, we have a European technical specification. which is for commercial applications. The work we've carried out here, was very much looking at the perceived outer edge of the use of water mist systems. Water mist systems are very good for flammable liquid fires, deep threat fires, local application, testing in compartments, so relatively small spaces. So we worked on the British standard looking at what would be called low hazard occupancies. And this has been named differently from ordinary hazard 1 because it's felt that with sprinklers you're looking at whole building protection, but with water mist you're often going to be looking at certain compartments within a building that you can protect. And in different areas you actually might need a different design of system. And so it's more of a room space protection arrangement. British standard is divided into 2 categories, category 1, 2 and 3. With category 1 picks up the FM type tests, and it's made for rooms of sort of 36 metre squared plan area. Category 2 again picks up the FM IMO type tests, and that can be used for larger spacings, but only to the fire loads that have been used within the test, so they're relatively low fire loads with less obstruction. And then the category 3 test, the BRE developed test simulated workstation, is intended for use sort of as the catch-all. So if you're unsure about the application, consider it as a category 3. So the backgrounds, so the test protocols come from FM and IMO, are very helpfully participated in the process, and the BRE trust report. I should say, I suppose, the tests aren't the same as the FM IMO. Some consideration has been made to Europeanise the standard arrangements, and also to take account of the fact that a lot of the standard tests done by others are 10-minute tests, but the real application would be sort of half-hour type applications, and so some of the way that the post-analysis of the results in terms of whether the temperature is being controlled it is assessed, not just a single temperature as the pass-fail criteria. So I don't know whether you're familiar with this, I won't dwell on it. So just to give you a feel, this is the bunk bed test used on board ships. So that's used for the small compartment. The large compartment test is that, I don't know if you saw that corner arrangement I showed you earlier, is a corner arrangement with plywood, foam, and a heptane and wood crib firing corner. The open space test for the category 2 is this sofa arrangements also used IMO FM, IMO now, these are foam sofas that stand 1 metre tall, and then a place between 4 under 1 nozzle, between 2 nozzles. And you're checking you've got proper coverage and proper control of that fire load. And then, as I've already shown you, the simulated workstation, which follows the same thoughts in terms of the safety test between 4 under 1, between 2. The acceptance criteria we've chosen, and it's based on our witness results, is that the plywood should the damage should be extended to the wall, shouldn't fall away, like the movie. Damage should be limited, and that ceiling temperatures should be below 80 degrees. So in summary, water mist, it is a complex technology. Water mist, what's lovely about it is it's a much more efficient use of water, but it has got increased vulnerabilities with this efficient use in terms of it can be blown away. The nozzle orifices are much smaller, then could be more prone to blocking if you don't get your engineering right. The industry, there's no generic system design. With sprinklers you have 5mm for an office, 10mm for storage at certain heights. There's no numbering system like that makes it easy. It's very application specific. You have to do fire tests for each application until somebody like you comes up with some much neater way of collecting different types of applications into a set. critical water parameters are nozzle and spacing, and then critical are the room or the application where it's going to be used. So what does the specifier need to know? They need to understand what the hazard that's going to be protected is, and they need to really appreciate that the water system does have limits in terms of the fire load where it's going to be used and the arrangements it's going to be used for. There we go, I'll finish there. So just the fun-wise, that was a research project on the, there's the YouTube site if you want to look at the video. We did the work and it was intended to be public domain information, so at least if you're looking to try and understand is temperature damage all reported, so you can have a view, an overview of how water system performs against Class A fires. And I'll stop there. Thank you very much.